So the goals for today are really didactic. So the idea is to try to give you a background of NeuroMechFly as a model, show you where you can find these resources, and incidentally, all of this, including this video, should be posted on our website after the workshop, so you can return back to it, including the slides, give you an overview of how we've actually used NeuroMechFly most recently, and then in blue we have the actual on-the-ground work, installation, and helping you to perform your own simulations. So the last part of this workshop is going to be, you just trying to implement things you find interesting. Okay, so why NeuroMechFly? This is the sort of historical aspect of it. So I'm not going to bring up Feynman, even though I just brought up Feynman. But there's this idea of reverse engineering, or what I cannot create, I do not understand. And the idea of reverse engineering is to disassemble or analyze something in detail. And as a biologist, we're all reverse engineering in the sense that we're disassembling or analyzing something in detail. Ideally, we discover important concepts regarding those details that we can translate to robotics, artificial systems, or to humans. But the neat thing about what we're doing with NeuroMechFly, and I think other body models, is to produce something similar, right? And we have several people here from laboratories that are trying to build Drosophila-inspired robots, and people working on simulations. And I think this is really one of the impetus for those works, is to try to produce something similar, to have impact in the real world. And so we're not the first people to generate insect-inspired systems. So this is an old video from Quinn's WEGS 2 robot, where you have these hybrid WEG, which are wheel or leg-like structures that allow this insect robots to travel over complex terrain. Of course, it looks nothing like the beautiful movements of a cockroach leg. As well, we've had simulations, 3D physics simulations of insect behavior. So this is from Ansgar Buskis' lab from 2004, where they built a model of the stick insect and have controllers based on what they understand about the underlying biology of the stick insect to drive movements of this controller. So this is not new, and indeed we also developed a much simpler model of Drosophila in 2017 that I'm not going to show you. But of course, the question is, why work with Drosophila instead of one of these other insects, right? We looked at the cockroach. They have this beautiful behavior where they can go over complex terrain. Stick insect as well can move on stems in nature. And of course, I think everybody in this room is aware that flies generate complex behaviors, and importantly, we can actually target neurons of interest. We have a small, compact nervous system, and these are really the properties that allow us to dig really deeply into the underlying mechanisms of control in the fly. So the first resource that I would refer you to is the first original NeuroMechFly paper in 2022. This is the work that first defined our body model, led by Victor Lobato-Rios, a PhD student in my laboratory. And what that entailed was taking a real fly, embedding it here, and then performing a CT scan of the fly. So at this point, we were really interested in moving beyond ball and stick models to much more complex models in terms of morphological realism. And part of the reason is that we eventually want to actually make inferences about what the real animal experiences in terms of the mechanical feedback with the environment, as well as, for example, if the fly is grooming, as you would be interested in the Simpson lab, we need to have real potential interactions between the body parts during collisions between the antenna and the legs, for example. You can't do this as well with ball and stick models, which motivated us to build this initial body model. So using this body model, we could actually do some really nice things in closed loop with real data. So here we have a fly on the ball. So we can make some inferences about the mechanical sensory feedback of this animal. So here we have 2D tracking, then 3D reconstruction, what we call kinematic replay, where we replay the behavior that we measured in a real fly, and then we can infer the collisions that occur between the different body parts of the animal. So this is one really nice early way in which the biomechanical model could be useful for science. But of course, if we want to understand how the nervous system works to drive behavior, we need something that can actually have neural network controllers as well. Which leads us to the paper that is now in press in Nature Methods and was published in bioRxiv, another resource where we describe basically what I'm just going to very briefly overview in the following slides of the improvements on the initial NeuroMechFly model. This is kind of busy, but effectively what you can see that we've added vision, olfaction, We've added as well the opportunity of using descending and ascending signals. We've added leg adhesion, the possibility for rugged terrain, as you see here in our new model, and that allowed us to do a variety of different things in terms of exploring mechanisms for neural control. Well, the first thing we wanted to do actually is to try to generate more realistic locomotion. So initially we had our locomotor controller driven by CPG controllers to try to emulate basically the joint degree of freedom ranges we saw in the real fly. Here what we did is we took a single step from a locomoting fly, performed 3D pose estimation, and then used this information to actually drive locomotion in the real fly. So the initial use cases were locomotor. So the first thing is by adding adhesion, we can actually have our simulation walking on increasingly slanted surfaces. Another use case that I'll just briefly talk about is that we have CPG-based locomotor control, or we can have feedback-based control. So this sort of dichotomy between distributed control versus centrally generated control with CPGs. Another use case was to add vision and olfaction. So in this visual object following use case, you can actually see what the simulation observes. So here we have the left eye and the right eye, the set of ommatidia, and you can actually watch what the fly is actually observing. So here we have this ball that it's following, and we're using a controller to actually follow the ball. In the olfactory avoidance and attraction, we have the fly walking through an environment and detecting this aversive odorant and being attracted to this attractive odorant. We also incorporated head stabilization, where we can actually, so if we observe our initial model walking through even flat terrain, we see that the raw visual experience is actually quite turbulent, but we can actually actuate the neck to try to reduce the turbulence in the way that a real insect would try to do that as well. We also use reinforcement learning to train a policy that allows our fly to try to reach an attractive orange odorant by passing this black pillar. You can see, again, visual experience of our simulation on the left and the right eye, as well as the olfactory experience as shown by the amplitude of olfactory input. Two more cases that were more biologically realistic per se. So this is actually an algorithm that's derived from Demir et al. eLife, where we have our fly walking through an odor plume trying to get to the odor source. So you can see a zoom in of what the fly is doing as it's trying to actually reach the source here. And finally, it's great that Srini just walked in. We take the Lenin model of the visual system and use it for our fly to actually track the other fly through a rugged terrain. So here we can see the left eye input, right eye input, and the activity patterns across an array of different sets of neurons. Okay, so additional resources that you could turn to, and again, remember that the slides will be available for you on our website. You just go to neuromechfly.org. One of the really valuable things that I think if you want to follow up on some of the work that we've already done is these tutorials, which follow through each of the points that I just showed you. Here are some examples. Interacting with NeuroMechFly, controlling with CPGs, rule-based controller, et cetera, vision, olfaction, path integration. So the hope is that after today, after installing things and trying them out, you can yourself just go home and try some of these tutorials yourself if you didn't manage to have the time currently.
So first, installation. The easiest way to get NeuroMechFly running is through Google Colab. Colab is this notebook environment that Google is hosting to a very large extent for free, and it's advantageous in many ways. You don't really need to set up a Python environment. We provided 2 blocks of boilerplate code by running which you can just set up anything that you need to run NeuroMechFly. And you can also get easy access to a GPU on Colab. It's not great though, because the computing power is kind of at Google's mercy. It varies from day to day. It's not really intended for sustained use. Like if you just leave the browser tab inactive for a few minutes or like 15 minutes, Google might just kill it. We have made this this template notebook. I'm just going to show it to you now. It's going to redirect you to this notebook. And as you can see, there's just one large block of code that sets everything up. So practically what you should do is to just go to runtime, change runtime type, which by the way is also written here if you want to read it later. And then you select the GPU, in this case a T4 GPU, and then it's going to connect you to a instance with the GPU, which we will use for rendering when you run the first block of code. And when you run the first block of code, it's going to tell you that this is written by us, not Google. And what's going to happen is that it's going to detect which system you're on, and it will take about 50 seconds, but it's going to set up the environment for you. And then you can just import it and then start implementing things. A better way to install FlyGym is, of course, to install it on your computer, whether it's a laptop or a workstation or a cluster if you have one at your institution. We recommend that you always create a Python virtual environment. This is because by doing so, you isolate FlyGym from any other project that you might be working on so that dependencies do not conflict with each other. FlyGym, which is the underlying Python library for NeuroMechFly version 2, is uploaded to the Python packaging index. So what this means practically is that if you have everything set up, you can just run pip install NeuroMechFly, and that's how you install it. Using this square bracket, if you type pip install FlyGym, if you type pip install FlyGym examples, it's going to install some additional dependencies that are not required to run NeuroMechFly per se, but they are required to run the examples that we have provided in the paper. So it's your choice.
Can I just interrupt with questions that I think probably people might have? So we have a really diverse group of people in this audience. Some people want to use it for educational purposes, or undergrads with limited programming experience, and others might want to do development. Do you have a suggestion for those two different sort of extremes about installation? Like, what's the easiest installation approach for undergrads, and what's the more advantageous for development?
Yeah, so the easiest way to run it is to just run it from the Google Colab link. If you want to run something small, that's great. Intermediate solution is to run this pip install FlyGym code. Like if you have Python installed or any kind of Python manager installed, this should be the easiest way. If you want to install it in the developer mode, so to say, if you want to actually change the code that we have written or improve upon it, then there's a more complex developer installation set of instructions that basically you just have to clone our GitHub repository, and that you can find online at neuromechfly.org.
So for people who are educators, is it clear what you should be doing right now? Or because I think that there's like a fairly large energy barrier for people who are not programmers or who are not focused on that. And sometimes if you provide too many options, it can also be challenging.
Yeah, so this demo that I'm going to do in a minute, we'll do it on Colab. So maybe everybody can just have a feel of how easy it can be if you're doing something really basic. So as I said, the next thing that we will do is to show a very minimal example of how one might control NeuroMechFly. So the control of NeuroMechFly is framed as a Markov decision process. Basically, you have a controller and you have a task. And this is in no way unique to neuroscience. The controller could be a chess engine and the task can just be a game of chess. Or it could be a controller for a robot or a nervous system for an animal, which is our case. The controller tells the task what to do. So what force should the muscle apply, or what is the, depending on your level of abstraction, maybe it's the activity of your motor neurons, and it could also just be the target angles of your joints, which is executed then through either a predetermined muscle model or some kind of robotic controller like a PD controller. In return, the task tells the controller what's the state of the system at this moment, which the controller uses to make the next decision. Optionally, the task also gives the controller a reward, which can be useful for reinforcement learning, for example. In our case, the controller is a neural network, and the task is just the control of NeuroMechFly. A more relevant version of it is the partially observable Markov decision process, where basically we don't have some kind of magical global access to the state. Instead, we have an observation from the perspective of the fly. For example, you won't have access to the absolute position of the animal as part of the state, but the animal cannot just somehow magically know its GPS location in the experimental arena. Another example is that instead of, you can still have access to, for example, end-effector positions, which is just where the leg tips are, but it has to be relative rather than global. And instead of information in general about the surrounding environment, maybe you can have visual input or factory input. This can be visualized alternatively like this. On the left of this figure, you have the controller or nervous system. On the right, you have the task, which is the interaction between NeuroMechFly, the body model, and its environment. Now, this is by itself not a very useful construction, just because everything is so high dimensional. If we think about it, the sensory input of an animal is almost infinite dimensional, right? You have every single piece of proprioceptive information, visual information, etc., etc. And in turn, the action is n-dimensional, where n is the number of motor neurons, which is a lot of motor neurons. So instead, we kind of built this intermediate level of abstraction, or this gray box that you're seeing, where you can hard code certain pre-programmed computation, either sensory pre-processing or pre-motor processing, which from a different perspective you might call post-processing of what the output of the controller is. And instead of choosing a level of abstraction as a developer of NeuroMechFly, the idea is that the user draws the box. The user decides on the level of abstraction, particularly the level of abstraction for different parts of the system. So for example, if you study the visual system, maybe you still want to close the loop because active sensing is interesting, but maybe you don't necessarily care so much about low-level motor control. So maybe you can just say, okay, the motor control part, like the walking controller, I'm just going to assume that is a coupled oscillator. So as a trivial example, we're just going to do something very simple. We're going to actuate all 42 leg degrees of freedom just with sine waves. So the fly will be doing just this. And then we'll record the joint angles in this process. In pseudocode, what this will look like is that first you initialize a simulation, and then you generate basically just 42 sine waves, 42 because we have 42 degrees of freedom. And then we initialize some empty arrays to record the history of actual joint angles. So once we have this ready, we can implement the actual simulation loop, where for every step I of the simulation, we apply the target joint angles at the ith step to the simulation as the action of our controller. Then we obtain the state observation from the simulation, and then we can append the current joint angle to the history. We can render the graphics, so we can have a video of the simulation, and that's all. We can terminate the simulation after. Time for our demo. So if you could just type this URL in your web browser, you should see something like this. As before, we click runtime, change runtime type, choose a GPU because that's going to help us render the image. And then we can start running the first code block. Just click this play button and run anyway. It might complain that you have too many sessions because it's Google's rule that you are only allowed one GPU session at a time. So just click manage. This was my older example. Just delete it. So if you just click the run button, what will happen here is that it will first, let me just zoom in a bit. It's going to first connect to an instance, and now it is running. This block of code is not so important. You can just ignore it. It's just setting up the environment. Based on version 1 of NeuroMechFly, we defined 7 degrees of freedom per leg. Those are thorax, coxa, pitch, row, yaw, coxa, femur, pitch, and row, femur, tibia, pitch, and tibia, tarsus, pitch. There are also a few joints between the tarsal segments that are compliant but not actively actuated. For convenience, we have already pre-programmed those degrees of freedom, so you can just import it, and it's going to tell you that these are the all leg doffs list of degrees of freedom that will actuate in this example. And now we just need to generate 42 sine waves, which we can do with NumPy. So here we have some parameters, like we're going to simulate half a second of fly behavior, the frequency of the sine waves of 5 Hertz, amplitude is 30 degrees, etc. We can visualize this. Basically, this is the control signal that we are going to have. With that, we can finally start to set up our FlyGym simulation. We start by creating a fly object. So from FlyGym, import fly, and then we can give our fly a name. We define the spawn position, so we are going to spawn the fly at 5 millimeters high, and then just drop it on the floor, as an example. We're going to actuate all leg degrees of freedom. That's our list of actuated joints. We can run this. And then we can create a camera object. This way we can record what's happening in the simulation. So similarly from FlyGym, import camera. By the way, I hope the code is somewhat self-explanatory, meaning that even if you're not familiar with programming in Python, just don't care so much about the syntax. It's not as important. Just try to read it as pseudocode if you're not familiar with Python programming. As I was saying, we create a camera, attach it to this fly. We will attach the camera to the left side of the fly, and we will, when we have finished recording, we'll replay this recording at 0x1 speed at 30 frames per second. This is just to tell the camera under the hood that actually you have to record at 300 Hertz. And then finally, we can set up the simulation itself. Import simulation. When we create the simulation object, we just tell it this is the list of flies that we want to simulate. In this case, it's just one fly, but you can have more. And this is the list of cameras. In this case, we have one. You can have multiple cameras. Another important parameter is the time step of your simulation. Essentially, what any physics simulator does is to integrate F equals ma over time. If we recall the high school calculus textbook, we just draw a lot of bins and under a curve and calculate the area under the curve. And the more bins you have, the smaller the bins you have, the more accurate it is going to be. But then the slower it is going to be. So in this case, I think we set it a bit earlier, but we are going to use 0.0001, so 0.1 millisecond to simulate. We can run this. As I said, NeuroMechFly operates as a partially observable Markov decision process. We're going to have a controller. We are going to have a task. The controller gives receives an observation from the task and gives the task an action. The task returns a new observation and a reward. In addition to this setup, we actually return 3 additional pieces of information from the task to the model, and this is for the modeler's convenience. The first thing is an arbitrary set of additional information. This can really be anything, like the fly. It's not observation because the fly doesn't have to, it's not necessarily something that the fly can actually sense, but maybe you want to, for example, obtain the raw readings of some sensors that has not been pre-processed in any way. Then you can put really anything in your debugging information. You can put anything in this additional information dictionary. The second thing is whether or not the task has been terminated because a goal has been accomplished. So imagine you're training a reinforcement learning task where the fly has to go to a specific location, and the fly went to that specific location, it's finished, and then you can just return true for this flag called terminated. Alternatively, there's something called truncated. This is kind of the same thing, except it's not because the task has been completed or succeeded or failed, but rather because of your choice as a modeler. So if the simulation has timed out, then you tell it it's not your fault, but the simulation is over now. We can get the initial observation and information dictionary by calling reset on the simulation. The observation is going to be a dictionary. In fact, it's a nested dictionary because the first level is which fly you want to get the observation of. Remember, we are allowed to provide a list of flies when we initialize the simulation. In this case, it's just one fly called Neuro. So we can just access it like this, and then let's see what keys we have in the dictionary. So we have some observation about the joint states, so position, angles, angular velocities, and torques. We have some observation of the fly itself, so global position, orientation, things like this. We have some information on the contact forces of the legs with the ground, and the effector positions, namely the leg tips, the orientation of the fly, the cardinal vectors showing the unit vectors pointing in the front, left, and up from the fly. From there, we can get an initial set of angles of the 42 degrees of freedom. So if we go to observation, neural joints, it's a matrix. On the top row of the matrix, it's the angles of all the degrees of freedom. This, of course, is not some information that you should just know by heart. This is all documented in FlyGym's documentation. So if I go to this link, we have a full specification of what the action spaces, what the observation spaces, etc. And now what we can do is to actually compute what we want the joint angles to be. So remember that previously we have just generated one sine wave, and now we know the initial positions, initial angles of all the actuated joints. We can just add them to the sine wave to get a 42 by 5000 vector, which defines how the angles should be, what the angles should be for each one of the 0.5 second times 10,000 steps per second simulation. And now it's finally time to actually run the simulation loop. We create an empty list called observation history, and then we can have a loop where we define the action, which is once again a nested dictionary in case you have multiple flies. In this case, the only thing in our action dictionary for neural is the target joint angles. But depending on what you are simulating, you can also have the on-off signal for example, leg adhesion. But in this case, it's just joint angles. And then we can apply this action to the simulation by calling simulation.step. This basically just advances the physics simulation by one step. And it takes as input your action. It spills out the observation of the next step, well, from the current step, the reward, whether it's been terminated, truncated, and this information dictionary containing arbitrary information. Don't remember to call render on the simulation so that we can render the frames from the camera, and then we add the observation dictionary to the history of observations. We're just gonna run this. This API, by the way, this standardized way of calling simulation.step and .render and earlier .reset, it follows a interface called Gym or Gymnasium now after it has been revamped by a different organization. And that's actually the namesake of our FlyGym library. Originally, it was intended to be a gym-compatible interface for NeuroMechFly. The advantage of adhering to this interface is that it kind of separates the problem of control into two parts. On one hand, you have, let's say, whatever the task is, and on the other hand, you have whatever the model is. And this is an extremely generic separation of the two components. On the side of the task, it could be motor control, but you could also be playing chess or any kind of thing that a controller can learn. On the side of controller, it could be any number of reinforcement learning algorithm, for example. So that's quite useful. In the meantime, the simulation has completed. Now let's just visualize the results. The solid lines indicate the actual observed joint angles of those degrees of freedom. And you only see 3 because a lot of them are just starting from 0. So don't worry. The dashed lines, on the other hand, indicate the target angles that we specified a bit earlier. So as I said, the joints have a finite stiffness. The actuators also have a finite gain. And this is like biologically true also, right? Like if I do this, but then I hit something, my kinematics is going to be different. So we have the time series here. We can also check the video. So if you run this block, it's going to generate a video. If you click this file button on the left, you can see it. And I'm just going to download this video.mp4 file here. So not very interesting. We just dropped the fly from 5 millimeters, and then it's just doing this silly dance.
I'm wondering, so for the previous plot, it seems that the deviation between the actual position and the target is only happening on one side of the sine wave. Is there any reason for that?
Yeah, it could be that I haven't really looked into it, but my guess would be when it's moving in a way that contacts the ground, there are some more reaction forces, whereas it's just doing this in the air, it's fine, it can follow the desired trajectory quite well. So far it looks like this is just some kind of fancy rendering platform, but it is not. Like, we're simulating actual physics. And as a result, you cannot just ask it to do just anything. There are movements that are generate such a strong force that you just can't, in real life, it doesn't happen. And in the physics simulation, the force is so great that it breaks the physics simulation. So as an example, if we go back to the beginning of the notebook and say, instead of oscillating at an amplitude of 30 degrees, let's say, do it at 90 degrees, which is quite a drastic movement. So maybe sometimes it's not, this range of movement is not even allowed, and we rerun everything. and we will run the simulation. What do we observe? Very soon, after 250 physics steps, it tells you that it first tells you that there's a warning, not a number, infinity, or huge value in one of the degrees of freedom is experienced, and the simulation is not stable. The current time is this. And then very soon after that, it breaks because the physics state is invalid. We can similarly visualize the time series. This time it's going to be very short. If we render the video, refresh. Yeah, so already without even hitting the floor, it was in such a weird pose that it just doesn't work anymore. So with this field example, what I want to say is that we're trying to simulate real physics here. Sometimes it's frustrating. That's, in my opinion, a good exposure of failure modes of either the biomechanical model or the controller model. Do we have any questions? Yeah.
What if you reduce the fatigue in this case?
It might help. I haven't tried. It's also tricky because at some point you stop gaining stability from smaller DT, because actually if the DT is too small, then numerical error dominates. You would have to go quite extreme there, but you know, it's very empirical. You just have to try it out. Any other questions?
So it's really time-consuming for you to have to go through playing every single subset of this notebook. Is there a way for people, when they make one change early on, to play through everything?
Yes. So normally, your notebook, you can just click runtime, restart, and run all, or run all as you prefer. In Colab, it doesn't really work with Mujoko because there are some open issues about this. It's unclear why this is the case. It has to do with how rendering happens, apparently. But you know, if you have installed NeuroMechFly and you're running it locally, then it shouldn't be a problem.
So which part is GPU involved in?
The rendering, yeah. So since Mujoko 3, there is something called MJX, which is a separate interface for running physics simulation, but with the GPU. We don't have it here because of some intermediate layer of dependency that that's not supported yet. It will be what I imagine would happen is that if you're running 1,000 simulations of 1,000 flies in parallel, then it's going to be super fast on the GPU. It's not going to take 1,000 times longer. Maybe it's going to take 10 times longer. If you're simulating a single fly in a single simulation, I think it might even be slower. I haven't tried. Previously, I have tried FlyGym, which is another GPU accelerated physics simulation platform. The optimal per simulation speed occurred when I was simulating around 1,000 flies at the same time. So the next notebook is going to be about kinematic replay of sensory readout. This part is supposed to be presented by our colleague Victor here. Unfortunately, he cannot attend SFN this year, but the slides that I'm going to present and the notebooks that I'm going to show are all from him. So in this part, we will show how we can replay behaviors that are recorded from real experimental data and how we can use that to infer dynamical forces from the simulation, as Pavan said. So what is kinematic replay? So it looks like this. On the right-hand side, we have experimental recordings of what a real fly is doing. Let's play it again. And if you pay attention, the fly on the left is making the exact same movements. Why do we do this? We do this because whereas we can infer the pose from these behavior recording videos, we cannot really infer dynamical variables like forces. So if I do this, you can see that I have my hand on the podium, but you do not know if I'm pressing really hard or just barely resting my hand on it. But maybe you can infer it better by seeing if I did this or very slowly this, right? So this would be, if I show this video, the fly is, we're replaying the behavior from the recording, and now you can see tiny little arrows whenever there's a floor contact, and then that just shows that you can infer the ground reaction forces. Same goes for joint torques as another example. Similarly, you can emulate the visual input of the fly. So these are from the two compound eyes of the fly. Each compound eye has between 700 and 800 what's called ommatidia, which are just the unit eyes of the insect compound eye. Yeah, so this is what the fly is supposed to be seeing when it's walking in this environment. It doesn't really have any features. There's a checkerboard floor. Those are all things that you can change. How do we do this? We have the experimental recording. From there, we can run pose estimation to get the 2D key point positions, and then you can triangulate the 3D pose from that. From there, you can infer the time series of joint angles, and then by applying those joint angles to NeuroMechFly, you get the replay of the same behavior. So if I can summarize this in a block diagram, to start, you have a potentially multi-view recording of the animal, and then you can run 2D pose estimation. From there, 3D pose, and then inverse kinematics. That's just the step where you go from XYZ positions of key points to actual joint angles. From there, you can replay it. Each step is kind of independent of each other. So for example, with 2D pose estimation, there are a lot of great tools nowadays to accomplish this. A few years ago, a former PhD student in Pavan's lab developed DFly 3D. There's also more general things like sleep or deep lab cut, etc., etc. For 3D pose estimation and alignment, there are also a lot of tools. With that, I just want to go to this other demo notebook. You can use the Colab notebook if you have NeuroMechFly installed already on your laptop. Then if you know how to do it, it could be easier if you just go to this GitHub repository and clone it, and then you just have all the notebooks that we need. Okay, so I'm not going to run this notebook actually, I'm just going to show you the results. So this notebook is about kinematic replay. We'll demonstrate how we can replay experimentally recorded flight kinematics to infer dynamical forces. If you're running it on Google Colab, do the same thing. Change your runtime type to a GPU instance. If you're not using Colab, you can just safely run this block of code, and it's going to complain that GitHub that FlyGym is not installed if you haven't installed it. Otherwise, it's just going to ignore. It's just going to do nothing. You can also run the second code block to download the kinematics data if it's not on your disk already. And then we are going to try to replay the behavior, the untethered walking behavior shown in this video. There's a few things that I'm not going to get into too much detail of. So for example, we define the physics simulation parameters. We load the data, the inverse kinematics data of the joint angles from this, and we shape it to the correct shape. This is more technical details that I'll skip. You can visualize this. So this is the actual, whereas we had sine waves, here we have the actual time series of joint angles. So the 7 colors are the 7 degrees of freedom, and we have 6 panels, 1 for each leg. Yeah.
How hard is the inverse kinematics problem if you increase the complexity of the joints? Like, just curious, like if you have active joints or like properties active feedback and so on, is the solution to the inverse problem stable and unique?
It's a great question. So inverse kinematics by itself, it's just about knowing where the end effector is. Let's see what the kinematic chain must be doing. Imagine I have a robotic arm. I know that the end of the robotic arm has to be here because I want to reach for something. And then it's just a matter of calculating what the joints must be doing to make the end effector there, right? This could be under constraint. If your robotic arm is like a snake, then there are many different ways that you can reach that pose. If you have many degrees of freedom or many compliant joints, it's going to be just intrinsically harder. You need additional constraints to get a unique solution. There's also another problem of scaling. Not all flies have the same body shape. Maybe this one fly has slightly longer tibia length, let's say, and therefore you're not going to have a perfect match to what NeuroMechFly can do. That's going to be also a bit tricky, so it depends on your setup. We have a variant of optics which we call sequential kinematics. It's developed by my colleague Pambeki Sam Ostel. The idea is that instead of doing inverse kinematics, which cares about optimizing for the location of the end effector, you actually sequentially do that for every key point. So it's some form of constraint. So going back, we have a bunch of joint angles, and then now the idea is to do exactly what we did in the last notebook, initialize the simulation, etc., except instead of getting data from the sine wave, we get data from this data block of experimental recording. And if we play the video, it's going to look something like this. Yeah, so the same behavior played at 5% speed. Now let's look at the observation space of what the fly is actually seeing. And those are just the dimensions of the different subcategories of the observation. I'm just going to say for the fly category, for example, it's 4x3 because we have the base position, base velocity, and they are both 3-dimensional in XYZ. Similarly, you have the roll pitch yaw, angles and angular velocities, and they are also 3-dimensional. This again is in the documentation. We have some more description of what this might mean for biologically, what sensory information you are actually deriving from this. I'm not going to go into so much detail here. You can read about it. And now with this replay, we can read out ground reaction forces. So those are the time series of the ground reaction forces for each one of the 6 legs. Similarly, we can read out also the joint torques. So this is just for one leg, I believe. Yes, for the left hind leg. For the 7 actuated degrees of freedom, you can read out the torque. But you can also do the same for the compliant passive joints on the tarsus. Those are shown in dashed lines. Another thing you can infer is the visual input. So these are actually the visual input of the two eyes of the fly. This is what the virtual camera mounted in the fly's eyes actually see. It looks slightly weird because it's very wide angle. The fly has a combined viewing angle of roughly 270 degrees. And we have processed that in a way that emulates what the individual eyes in the compound eyes might be seeing. It really depends. For this particular setup, we just use we have one camera, but then it's 3 views because we have 2 prisms, one on each side of the corridor where the fly is walking. So in this case, because the fly is untethered and we have the cardinal viewing angles, it's quite easy. 3 is okay. If you have a fly walking on a ball and there's a lot of occlusion, then depending on where you put your cameras, where the rest of your setup allows you to put cameras, like for example, if you have a 2-photon setup, it takes a lot of space already. It just depends. Any other questions? Yep.
So can you also do inverse dynamics instead of kinematics?
Excellent question. I think you can if you have some assumption of what the muscle model is. It's a bit under constraint because from motor neurons to muscles and from muscle to torque, considering that you have a set of motor neurons and you have a set of muscles to control the same joint, then it's a bit under constraint. So we're not doing it here, but if you have a reasonable assumption, a model of the muscle, then yes.
I'm just going to briefly talk about what we can achieve with the last notebook here. So for people who are interested in vision, this might be quite interesting. So this covers several functionality of NeuroMechFly. So first, of course, vision. This notebook also demonstrates how you can do multi-fly simulation and how you can use vision to control how they walk, for example. And finally, we'll also demonstrate how we can interface with other more realistic model, like instead of having some very simplified, maybe we can integrate the connector. So this example will try to make one fly follow another fly. The leading fly walk in a zigzagging way, and then try to, based on vision, to implement a really simple algorithm. So just basically threshold the Ommatidia reading, and then compare which side is darker, and then just turn to that side. And so you can based on this notebook, so feel free to play around, maybe implement your own algorithm. Here's the link for it. In this example, we're trying to implement following, so which involves turning. So we'll first go over how we can implement a really simple model of turning. So we start off with simple CPG control by modulating the amplitude of CPGs on each side of the body. So for example, if you try to amplify the movement on the right, then you are going to make the fly turn to the left. So we also have one notebook specifically explaining CPG control, so feel free to also check out the tutorial for more details. And so here we implement a really simple model of turning. Next we'll go over how we can perform multi-fly simulation. So essentially it's by passing a list of flies. So last time when we have only one fly, so now we can just add more fly to the list when we create the simulation. So here, that's basically the difference. And instead of using the base fly, then we also use a fly that implements the turning. So these are all have been pre-implemented. So you can just import it from the package. And this will also show you how you can visualize trajectories. and also how you can try to infer what the fly is seeing. So for example, this is how another fly would look like on the retina, and you can also look at like the raw vision version before like passing to like the retina. And here's an example. So we just compare how many ommatidia gets activated on each side, and turn to that side accordingly. So in the end, you get something like this basically. Like they will now be following each other.
So in both of these cases, in each time step, you're calculating new behavior for each of these flies. So you can have different controllers for different flies, for example.
Yes. So the leading fly is just walking based on a square wave descending drive. It would like have 0.25 seconds of large amplitude of CPGs like on the left, and then so they will turn to the right and then turn to the left. So and then we'll actively control the fly behind it to try to follow it based on vision.
So in principle, how does this scale? You get 3, 4, 5, 10 flies. What happens in terms of speed of simulation?
For now, it's roughly linear. So yeah, like if you have more flies, then yeah, it's linear. And if you're feeling ambitious, you can also try to incorporate the connectum constraint vision model from a recent Nature paper from Janne. And so here we can just try to interface with the model with ours, which is actually relatively simple to do, and it has already been implemented. And so in this case, you just need to replace one of the fly with this realistic vision fly. So now the vision has been replaced by this model, and then you can do really cool things like inferring the activities of different classes of neurons in the vision system. So for example, here's the results in our paper, but you can see that so these are the activity of different classes of neurons, and then based on the activities we can implement also another controller to make the fly follow one another.